So our final section on Module 8 has to do with power. And so we talked a little bit before about this being the James chapter. And so we already had James Prescott Joule, who the unit of work is named after. And we also have James Watt, and he gets the unit for power. So power has to do with the rate at which work is done. So that basically means work over change in time. And so if we remember that work is the cosine of the angle times the force and the displacement, you could also substitute that in there depending on what you're given in the problem. So we're going to look a little bit at a power rating. Most of the time when we're talking about watts, we're talking about light bulbs or energy, but we could be talking about anything. So I do have a trusty assistant who's going to help me with this today. And so we have a tired college student somewhere. A tired college student. There she is. The tired college student is going to do some push-ups. So for 2 seconds, this tired college student is going to do some push-ups. 1, 2. Look how exhausted she is. We should send her back to bed. Goodbye. But we can figure out the amount of power that she used if we know how much work she did. So we'll say that she expended 0.5 joules of work, so we know that's our work. And we counted off the 2 seconds, so we know our time is 2 seconds. And so we can calculate her power simply by plugging and chugging. So we put our 0.5 joules of work over our 2 seconds, and we found that she expended 0.255 watts of power. So hopefully we won't ever have to use her to run our electricity. So
that's so mean.
Sorry. So that's pretty much how power works. So you just have to remember that you can substitute in if you're given a force and a displacement. You remember you want to find the angle at which that was done, and you can replace that for your easy joules that you were just given in this kind of problem. So if we talked about maybe an escalator moving up, an escalator can take people up and down at the mall or the airport or wherever. You all are familiar with that. And so if it can go up to the second floor, which is 5.2 meters away, I'll get rid of my college student math here. And we have our escalator going up. And it goes up 2.5, I dyslexed that, sorry, 5.2 meters. And it can take 20 people. I'm not going to draw 20 people. I'm going to draw one person here times 20. It can take 20 people at a time up that 5.2 meters. And we'll say that the average person's mass is going to be 54.9 kilograms. We want to know how much power is going to be required to get all these people up to the second floor. Okay, so let's look at what we have. So if we know that the work of one passenger, we'll just look at one passenger right now. The work to do one passenger is going to be its force times the distance that it goes times the cosine of the angle. We can figure out that since it's actually applying a force in that direction, and that's the direction of the motion, that we don't really need that. That's going to be the cosine of 0, which is 1, so that makes us happy. So we know that the amount of work is going to be mass. So this is going to be mass, which is 54.9 kilograms, times the acceleration of gravity. That's how we get the force on the object. And it's going to move 5.2 meters. So we can determine the mass to move one person is going to be, we'll say 2798 joules. And so then if we have 20 passengers, that would be 55.5 joules. So this is one person, and this is 20 people. That's how much work is done. But what we want to know is how much power is that? So if we figure out our work, we want to know how long it takes. And we're going to say that it takes 60 seconds to go all the way up there. So we can do our work divided by 60 seconds. And that will give us a power rating of 933 watts. I didn't make that up. I was given that in the problem. I forgot to read that. So that is power, work at a rate of time. Okay. See you guys in class.